Okay, class. Section 4.7, Use of Isosceles and Equilateral Triangles, Part 1. There are 2 videos for 4.7, but there will be 1 homework. So do not do the homework until you have watched both videos. All right, so a quick review of what isosceles triangles are. It's a triangle with 2 congruent sides. So if we have a triangle that has 2 sides congruent, we know it's an isosceles triangle. So what can we do with that information? Well, we have the base angles theorem, which states if we know 2 sides are congruent, if we know AB is congruent to AC, then we know angle B is going to be congruent with angle C. It just has to work that way. Those 2 sides that are congruent, the 2 angles that are not in between. So notice angle A is that included angle. It's between the 2 sides. We're not talking about that angle. It's the other 2 angles are going to be congruent. We call them base angles. So if you reorientate your triangle so that those 2 sides are pointing up, the 2 angles that are on the ground are your congruent ones. We also have the converse of base angles theorem. And that is, if we know the angles are congruent, we start off knowing those base angles are congruent, or any 2 angles, then we know that those 2 sides are going to be congruent, that AB is going to be congruent to AC. So that's the converse. Remember our conditional statements and our converse, they are flipping the hypothesis and conclusion. So looking back at that base angles theorem, that's our conditional statement. We know the sides are congruent, and then we know those 2 angles are congruent. The converse is if we know those 2 angles are congruent, then we know those 2 sides are congruent. So because we have both the conditional and the converse as true, we can make a biconditional statement. Remember those if and only if statements we made? We can make those if both conditional and converse were true. Now what we've added here is a corollary. Simply what corollary means is that there's some additional information that we can conclude easily. So corollary to base angles and corollary to converse of base angles theorem is this, that a triangle is equilateral if and only if it is equiangular, or we could flip those around. If a triangle is equiangular, or a triangle is equiangular if and only if it is equilateral. Since we're able to say that 2 sides are congruent means that 2 angles are congruent, then it logically follows that if all 3 sides are congruent, then all 3 angles are going to be congruent, and vice versa. If we can state that 2 angles are congruent, or if we can see that 2 angles are congruent so we know 2 sides are, then it logically follows if we can say 3 angles are congruent, then we can say 3 sides are congruent. So a triangle is equilateral if and only if it is equiangular. So if we ever see an equiangular triangle, we know it's also equilateral. If we ever see an equilateral triangle, we also know that it's equiangular or regular. Now this doesn't work with other polygons, it only works with triangles. So you can have equiangular polygons that are not equilateral and equilateral polygons that are not equiangular, but you can't have that with a triangle. If it's equilateral, it is also equiangular, and vice versa. So let's look at these examples, and then that'll be the end of part 1, and then you can do the other examples in part 2. So examples 1 through 4. We want to copy and complete the statement and tell what theorem or corollary we use. So we're just going to fill in the blanks and then tell what corollary or theorem we use. If AE is over here, If AE is congruent to CE, then, and this funny little symbol that looks like a curved E with a line through it means angle. Then with the base angles theorem, we know that angle there at A and the angle there at C are congruent. But since there's multiple angles at those vertices, we need to use 3 letters to name them. So looking at my first one, I would call that EAC. Angle EAC would be congruent with angle ECA. And that was the base angles theorem. We knew the sides were congruent, so then it followed that those angles were congruent. Okay, let's look at the next one. If angle DAE, I'm going to erase what we previously did. So I'm looking at angle DAE is congruent to DEA. So DAE is congruent to DEA, that's going the other way. Then it follows that we're talking about these sides, AD and ED, being congruent. So then it follows that side AD is congruent to side ED. And that would be the converse of base angles theorem. Converse of base angles theorem. If we know those angles, then we know those sides. Okay, looking at number 3. We see if angle BDF, that would be that angle, is congruent to DBF, that angle, and congruent to BFD, that angle, then we can say that all 3 of those sides are congruent. Side DB congruent to side BF, congruent to side FD. And that would be our corollary to the base angles and corollary to the converse of base angles theorem. So I'll write that down here. So that's corollary to base angles and corollary to converse of base angles. So then number 4. If we can say side AB, that's this large side, is congruent to side BC, that's this large side, and congruent to side AC. So we're looking at the large triangle. Then we can state that these angles are going to be congruent. So this angle, and we would have to use 3 letters again to name it since we have multiple angles at this vertice, BAC. But then whenever I name this angle up here at B, there's just one letter or just one angle up there. So that's just angle B. And then the other angle, BCA. So showing that those sides were congruent, we could then state that those angles were congruent, and that reason is the same corollary to base angles and corollary to converse of base angles theorem. You would write that same reason. All right, that's it on part one. Just to break it up, keep the examples in one place and the definitions in another. So watch 4.2 for those other examples. Make sure you watch both videos before trying that homework.